Welcome back, Mindsetters. Thank you so much for your awesome interaction on the page. It's great to see that you guys have actually recovered from the relaxing weekends. If you want, you can even tell me how your weekends went because I know that it was awesome because, weekends are always more awesome than the week. I wish that the week was Monday to Friday, the weekend was Monday to Friday, and then during the week was just Saturday and Sunday. I think that'll work much better for me. How's it for you, Iti?
Great. Let me just carry on. I want to take more illustrations, from my preparation here and try and explain it. All right, what I have here are two graphs. There are some times where you put money in the bank, but now and then you get tempted to go and withdraw, or you are under pressure to go and withdraw because there's a disaster at home or something, right? So such withdrawals tend to cause a discontinuity in your investment. So what I have here is a graph that shows how an investment can grow. It typically would have grown, let's say, exponentially. Pick another pen here. All right. So you would have had your investment growing exponentially, but because of this kind of discontinuities. So over here, you've got, in fact, this one is not a withdrawal. A withdrawal is over there. So I want to mention that either you've got withdrawals or you've got, you decide that you're going to top up. You're going to top up what, you invested in the beginning. So that causes a discontinuity, an immediate increase in the investment. All right? And at that point, you've got a new amount which will then grow in its own period. Until you disturb it again, let's call this TP, and then this one TP plus 3, let's say. All right. So what happened in this case is that your money was growing and you decided, I've won a lotto or something like that, and you decide, I'm going to put this lump sum as well into this account. It must grow together with, now that raises your amount to a new value there. Okay. A new accumulated value. And as it is growing, you decide that you're going to withdraw a certain amount to go and use it for whatever you are under pressure to use it for. All right? And that suddenly drops your amount back to, let's say, that level. And now, from that point on, when your money grows, it grows on a lower balance, and it will continue to grow in that sense. And what you're having on the right-hand side is another illustration whereby you are repaying your loan. You had a lump sum given to you because you wanted to buy a house or you wanted to buy a car or some other big item. You didn't have, all the cash at hand. Then the bank gave you that much. What will happen is, if you look at the loan amount itself, they will charge you interest. Look at it growing separately from your repayments. So treat your repayments, your loan as growing from this point to, following that curve. Now, you start putting payments to try and bring down the balance. And what you'll notice is that you didn't put anything in the beginning, but you start putting something, then your money faces the same interest rate and it grows. There will be a point where your repayments cross over with the growth of your loan amount. As the loan amount grows, your repayments are growing as well. Then you get a point where the two cross over. It is at that point that you basically finish paying for your loan and you settle the whole thing. Now, what I have as the third curve there is what I call the loan balance curve. What it means is that at this point, your balance is exactly what what the bank gave you. And as time goes on, the difference between the two green graphs that I've illustrated there is represented by this line, the points on this. Okay, until the difference, as you can see, these are the differences. They will keep reducing until the difference is 0 and you have repaid your loan. All right, and what's the other thing? You had a question about
Yes.
effective interest rate.
Yes.
Yeah. hopefully that
Simpiwe asks, and someone else just asked as well, how does one differentiate between nominal and effective interests and the formulas?
Okay. Let me just extend this page and do it thoroughly, the other one. So what you are having normally is that an accumulated amount for compound interest is given by P into 1 plus I to the exponent n, the number of periods where they charge you interest, where they calculate interest. Now, another thing that you'll hear very often is compoundings. This effective interest rate is going to depend on what the compoundings are. Typically, if I can draw a table here, where, let me use capital N for number of compoundings, and then work out what the, let's say the interest is, okay, the accumulated amount is going to be. So what's going to happen is if n is equal to 1, this period is basically 1 year, and it's just the same as that. So typically we talk about half-yearly compoundings, and when you have half-yearly compoundings, you will have 2 periods in which they calculate your interest. And if I can write here, half-yearly. So compoundings are half-yearly there. Compoundings in this case are annually. Then the 3, no, that's not a favorite. Typically you have quarterly compoundings, and if you go quarterly compoundings now, you will have 4 quarters out of a year. Remember, half-yearly meant 2 half years in 1 year. All right, so if I move on, what's the other one? This is quarterly, yeah, quarterly.
Can you get monthly?
Yes, I'm just growing it, you'll see.
Okay.
The next one is, in fact, the next one is, yeah, is monthly. Okay, so monthly is the next one. So this should be enough to illustrate the effective interest rate, and I'll explain what it means. Monthly, you've got 12 months in a year. Now, if I said to you, I'm giving you a loan at a nominal interest rate of 9%, let's choose 9%, and I tell you that I'm going to compound it annually, let's say, or let's say half yearly. So the formula that we use for the accumulated amount becomes P into 1 plus. Now, notice that your interest must now match the period. Okay. This capital N, we said, is the number of compoundings. So in other words, if I want to charge interest on a monthly basis, I'm going to divide by 12. And now, if this was just 1 year, then 1 times 12 would be equal to the number of months in that year. All right. So for this, for us to be able to compare this quickly, I think let us take n equals to 1, the small n. For n equal to 1 and the interest, nominal interest. So this nominal interest is basically what the bank will always quote for you. Nominal, that's what they, you need to have a bottom line when you define anything. So in this case, interest rate, the banks use 1 year as the period, which they quote for. So in this case, we said 9% per annum. And this was our nominal interest rate, nominal. All right. Now, if I want to see what I'm paying effectively at the end of the year because of the compoundings, I can then compare the accumulated amounts using the two equations. So in other words, I can equate them and see what I'm getting in the end. So I'll come back to that when we calculate that. So what we are having is the accumulated amount. We said if we just look at annual compounding, it would be 1 plus 0.09, that's to the exponent 1. That should be equal to, if I now consider the compoundings, I will put 1 plus 0.09, and I now, like I said, have to divide by the number of compoundings. And this is going to be 1 times n, okay, capital N. Capital N I'm using for number of compoundings then. All right, so if I look at this thing, it means that P is out of the picture. I'm going to compare the, what I get when, what's that? I'm going to compare the value that I get depending on the number of compoundings that all right, divided by n. Was that 1 plus 0.9, not 9? Okay, let's erase that. So in this, I want to calculate 1 plus 0.09 divided by the n, okay? And to that, I'm going to raise it to the exponent n. All right, so let me just work out the values here. If I take the calculator quickly, let's see, 1.09. For the first one, it's simply 1.09 to the exponent 1 in this case. There is 1 compounding. So not a problem. There you can see, I want to have another column there. I want to see how much more am I going to pay in terms of extra interest. So in this case, it's just 9%. That is what you call effective interest rate. So you will see how it will illustrate here. I effective. I want to see what these values will be as I change the compoundings. All right. For this one, I'm going to have 1 plus 0.09 divided by 2. All of that must be raised to the exponent 2. And if I work it out quickly, 1.0, okay, where is that? Delete that. So I want 1 plus, open the bracket. It's not active. All right, let's see. All right. That, let's see. That, yeah. All right, let's see that. Yeah. Okay. So if I work on 1 comma. Okay, close that.
I think it's that cross there in the corner.
That's right. I do it
Yes.
again.
There you go.
All right. So that's 1 plus.
Is it not working still?
Okay. All right. Let's see. This thing is a bit revolting there. 1 plus not comma not 9 divided by 2. All right. If I close the bracket there and I raise this to the exponent 2, what do I get? I get 1.092. So the extra bit that you have there is going to be, close that. All right. It's going to be 92. Right. 9.2%. All right. If I then go and use 4 in the place of 2, let's see what I get. It will be a different value. It's going to be, open that, that's 1 plus not, comma, not 9 divided by 2, and a close bracket. I raise that, divided by 4, by the way, because I'm on 4 now. 4 compoundings, and I close that, and I raise that to the exponent 4. All right. Right. All right. So that is to the exponent 4, if I'm not mistaken. All right. Okay, so that is to the exponent 4. And what does it give me? It gives me 9308. Okay. 9. Okay. Right.
And just
Okay,
click
click
on the
that.
corner again there. In the corner, the red cross.
All right.
Yes, and then click the red cross on the calculator.
All right.
Yes.
Okay, that's right. Sure. 9.09. This was 9.3 now. All right. This one was 9.3. I'm sure already the illustration is beginning to shape up, because you'll notice that we started off with a compounding that was 1, and you paid, if it was 1 rand, you paid 9 cents extra. In that case, you paid slightly more, and it keeps increasing depending on the number of compoundings. I think I can go to the next one that says 1 plus not comma not 9 divided by 12. Now, that is to the. All right. Okay, so what will happen is you will then have this as the effective interest rate. I hope this is going to help in illustrating what effective interest rate does as compared to nominal interest rate. So the moment you're quoted the number of compoundings, you can imagine that they quote you, say, 365 days as, the compoundings. Which means you are now going to have to divide by 365 and then work out the period. It must correspond all the time. The interest that you charge, if it's per day, then you must count in days. If your interest is in half years, you must count in half years. How many half years do you have? If it's quarters, how many quarters do you have? So essentially that's what nominal interest rate differs, how it differs with effective interest rate.
With effective, okay, cool.
Yes.
And then we forgot about daily. Daily is also 365.
Daily, that's why I say,
yes.
you could divide by 365.
Yes,
Yeah.
okay.
You
Okay,
know.
thank you
All
very
right.
much for that. So that is that up there that you have written,
Yes.
is that the formula that they would use to find the nominal?
Now, if I combine these two, okay, now, let's say you're given the nominal interest rate. Let me just move on here. Where am I? All right, if I now take if I compare the two amounts without compounding and with compoundings, So you'll notice that I end up with 1 plus interest, okay, equal to, if I just take 1 year, okay, this is to the exponent 1. So equals to, on this side, it would have been 1 plus, what's that, interest over n, all to the exponent
1.
n like that.
Oh, n. Okay.
Okay. So when you rearrange this, now we call this the result that we get, you know, when we rearrange this, we're going to call it I effective when we look at the compoundings. So it's going to be 1 plus I over number of compoundings to the exponent number of periods, and you take away the 1. That is what, this is the formula that many will come across.
Okay.
Easy to derive.
That
you know,
is.
because you're just comparing without compoundings with compoundings.
With compoundings. Okay, that makes
Alright.
sense.
Great.
That makes sense. Thank you, Iti.
All right.
Thank you guys for such an amazing show. You guys were awesome today. The questions, as I say, always show that you understand. So now we know that you understand because you ask really good, concise
Ah, they were
questions.
good questions.
Also, yes.
Yeah.
Also to Liberty. Thank you, Liberty, for an awesome show. You know we love Liberty, guys. So make sure on the page you also give a shout out to Liberty. Thank you, guys. Remember, if you have questions, you can keep asking. I am still on the page. Shout out to all grade 12 because it is their turn next. But see you grade 11s for maths next week. Bye-bye.